In this video, I'm going to relate an idea for a new impulse drive design that I have not yet been able to try myself. Though I haven't been able to do an experiment to actually test it yet, I want to make a video about it because of how interesting I think it is. You can have a closed system oscillate under a sinusoidal force, in this case according to sine of theta, such that the cumulative integral of that sinusoidal force results in pulses of velocity according to this picture. Thus, it is possible to design a closed system that the internal oscillations can have an average velocity but will have no average force acting on the system, since the average value of sine of x is 0. We could force the sinusoidal oscillations to acquire an average by two methods. Firstly, you could add a DC offset to the sinusoidal function. This would be equivalent to having a constant external force act on the system. The second way is you can bend the sinusoidal function through phase modulation. If the force acting on the system is a composite trig function instead of just sine of theta, the force now will have an average value without the function explicitly having a DC offset, because its peaks and valleys are different shapes due to the changing period. It's possible to construct a closed path such that the derivative of the y component of the tangent vector to that path is this composite trig function. We do this by first defining a force along the y direction as being this composite trig function. This is the y component of force acting on the path, or equivalently, through conservation of momentum, the reaction force acting on a mass constrained to traversing the path. If we cumulatively integrate this y force with respect to theta twice, we get a y position. If we arbitrarily set the corresponding x position to cos theta, we end up with this path. This isn't a closed path, but that's because we have not properly accounted for the displacement that a mass traversing this path would cause this path to have if it was free to move. For example, for a car to traverse a turn, the car's velocity has to change, which even if its speed does not, can only be accomplished through a change in momentum or acceleration. This means that a force must be exerted on the car to cause it to turn. By symmetry, the car also exerts reaction force on the thing causing it to turn. In the example of a car, this is the road. But if the road itself was placed upon a frictionless surface, the constraining of the car's motion to the path of the road will also impart momentum onto the road and cause it to move. In short, to close the path, we have to get back to a stationary frame of reference by transforming the points that define this path. With some trial and error, I simply discovered that this is pretty close to making a closed loop. This picture is the resulting path. It's not perfect, there's technically a small gap at the top right, but it is pretty close. We can extract a new y component of force from this closed path by finding the tangent vector between each point along it and taking the derivative of that tangent vector with respect to theta along the path. The result is the first graph. It retains the same general shape as sine theta of cos theta, but rescaled. This also has a discontinuity at the end because the path isn't truly closed the way I have defined it. But if you get rid of the discontinuity and rescale it, it is almost exactly the same as the original composite trig function for the non-zero average force. This all means that if we constrain a mass to traversing this path, the reaction forces created in doing so will have an average y component, meaning that as long as you keep giving the system energy in the form of periodically or continuously accelerating the mass, the track will also accelerate in the y direction. That's all for now. Thank you for watching.